Good morning. Good morning, everyone. If you could take your seats, please. Nous pouvons commencer maintenant. Well, thank you very much, and welcome to the plenary session on the state of knowledge on climate change. I'd like to say, first of all, that the speakers at the opening plenary that we had the pleasure of listening to really spoke very strongly and very well and informed about the state of climate knowledge around the world, and I was very pleased on their presentations. As I said to the minister, I will wish to quote them when I'm speaking in Canada later. I think we have a very interesting session now on the state of knowledge on climate change as presented by a series of climate experts. Unfortunately, Richard Mayunge from Tanzania, for health reasons, is not able to be with us, so we will have a slightly flexible time, Fred, not much, but slightly more flexible than earlier planned. I should introduce myself. I'm Gordon Mcbean. I'm the president of the International Council for Science, and we are, as the International Council for Science, are very pleased to be an international partner for this very important conference. So we very much appreciate the French government and the organizers for involving us fully in this. Our mission with the Council of Science is to strengthen science for the benefit of societies all around the world, and we work across the disciplines, across the issues. The science that we're talking about today is climate change, and this is an issue which the Council of Science and many of our partners here have been involved with for many decades. In our case, goes back before this, but in 1957, the International Geophysical Year started the initial fundamental observations of carbon dioxide, ozone, the launch of satellites, Sputnik, for observing our Earth's atmosphere. And we partnered later to create the World Climate Research Program with the World Meteorological Organization and the Intergovernmental Oceanographic Commission of UNESCO. And I think we will have a speaker, Thomas Stocker, who is now the co-chair of Working Group 1 of the Intergovernmental Panel on Climate Change, which role has been to assess science. But the science that they are assessing has been done, not entirely, but largely by programs such as the World Climate Research Program, the International Geosphere-Biosphere Program, and other programs like that, organized by the international science organizations, the Council of Science, the Social Science Council, WMO, UNEP, UNESCO, UNU, UNEP, I probably forgot a few, but anyway. The important thing is to bring all this together, and that's why we have this new program, Future Earth Research for Global Sustainability, which will build across the issues. Climate change is a huge issue, but it needs to work with and be seen in the context of sustainable development goals, of disaster risk reduction, and those kind of issues, and in the terms of the big data that we produce in all of these. So these are the issues we're going to be dealing with collectively over the years to come. But to this morning, we're going to talk, as I said, about the state of knowledge on climate change. We have, as I said, unfortunately, one of our speakers is not here, but we'll hear from our speakers the issues of the summaries of science as we know it, the Intergovernmental Panel on Climate Change, look at the future of climate science, getting into the impacts on a regional through to global scale, the Arctic issues, the role of greenhouse gas emissions, and then discussing the huge issue of climate disasters in a panel discussion at the end as to how these affect people in developing countries, small island states, coastal zones of all countries, etc. So we have a very, I think, exciting set of speakers this morning. We want to allow them their full time to speak, but I really want to, I guess I'll have to keep them on time, but I wanted to first of all introduce Jean-François Susanna, who is helping me with all this organization. He's doing all the real work. I'm just up here giving the talks. But importantly, he is a member of the scientific committee for this conference, and I really thank all the organizers. Chris Field, I saw somewhere up front somewhere recently. Anyway, we've put together this very exciting program. So with that, I would like to say what we're going to do is, first of all, have 2 keynote speakers, and they're both on the podium with us now. We will then bring in the 3 highlight speakers and then the panel discussion. So with that, I would like to, first of all, introduce Thomas Stocker, who is with the Physics Institute of the University of Bern in Switzerland. I should claim some credit that he did his PhD in Canada with a mutual colleague of ours. And he will talk about the synthesis of the IPCC assessment report number 5. So with that, I'd introduce Thomas to be our first speaker.
Thank you very much, Gordon. Ladies and gentlemen, colleagues and friends, it's a great privilege here to give the first keynote to this memorable conference. And I should start by expressing my gratitude to the organizers, my French colleagues, and the entire scientific steering committee, who have assembled an excellent program here that encompasses, I believe, the whole breadth of climate science and touches on all points that are relevant in the scientific preparation towards COP21. I think it's very timely to hear the voice of the science again at this time here after IPCC has delivered its 5th assessment report and all the related products. And it is not myself only who presents this presentation, but I'm sure I'm presenting that on behalf of all the colleagues who have worked so hard in the past 6 years to assemble this unique assessment under the wings of the Intergovernmental Panel on Climate Change, organized in 3 working groups, but reaching out much further beyond just the selected lead authors to many, many thousands of contributing authors to provide the knowledge that the political decision makers actually are calling for. We've heard impressive testimonies this morning about the need for scientific evidence in this huge problem, and it's with pleasure that I go through the most important results as they were highlighted in the summary for policymakers of the synthesis report. And I'm not sure whether I do have the first slide here. Perhaps if we could get that, that's right. So I will be talking a little bit about the synthesis report, but before I do that, just permit me to remind ourselves what the most important products are from our 5th assessment report. These are 3 comprehensive reports on the physical science basis, on impacts, vulnerability, and adaptation and regional climate change, and the 3rd on mitigation of climate change. But in addition to that, 2 special reports have also been presented to the panel, one on renewable energy sources and climate change mitigation, and a second one jointly by Working Group 2 and Working Group 1 on managing the risks of extreme events and disasters to advance climate change adaptation. But as you colleague scientists know very well, beyond all these reports and written documents, there has been really a series of important workshops and expert meetings in the preparation of these assessment reports in all working groups, sometimes jointly, sometimes very focused. And I think it's that effort that provides the glue in the scientific community to not only prepare for the assessments, but also to carry much longer forward in research programs that are being established, that are being informed by these extremely fruitful meetings. The whole effort obviously culminated in the preparation of the synthesis report itself, a great experience from my perspective, bringing together the hard-working 3 working groups into one single product. It's a huge effort, as you can see here. We have produced these 3 comprehensive reports, 2 special reports. I've counted over 7,500 printed pages, and I don't want to go into all the numerology, but this one here has been distilled in the summary for policymakers to just 31 printed pages. And obviously, policymakers still have a hard time to read from the start to the end, the 31 rather complex pages with many diagrams, 14 in total. And therefore, we also, for the first time, tried to summarize what has been assessed over the past 5 years in short and succinct summary statements. All in all, there are 21 headline statements, which altogether print on just 1 sheet of paper, admittedly both sides. So I would argue here today we are at a time where no policymaker can say that they have no time to absorb the messages of IPCC from their first assessment report. And there is a time where nobody has an excuse not to understand what the messages are. I should give tribute to all the individuals, and I've seen many of you here present now at this scientific conference who have contributed either as coordinating lead authors, bureau members, and many other functions in this unique journey that started in 2008 and ended in November 2014 with the publication of the synthesis report. It has gone beyond that. I mentioned already the contributing authors, all of which are listed in the 3 reports, which play an extremely significant role in an assessment because they are the root system into the scientific community, which allow us to present a robust and transparent assessment, a scientific assessment, which is the task of the IPCC. So let's now recall a few of the important results that have been worked on in this assessment. First of all, thanks to millions of measurements and large-scale observational programs, we are now extremely well informed about the change that this planet has gone through in the past 160 years. You see on top the increase of global mean temperature based on several data sets. You also see the increase of the average sea level change. The numbers, 0.85 degrees Celsius global mean since the beginning of the 21st century, and 19 centimeters of sea level rise as observed around the world in the global mean. What you see here is one of these headline statements, and it gives testimony to the fact that the changes that we are measuring with our systems have to be put into a historical context. And in that context, we are confident to say that, first of all, the warming that we see is unequivocal. And since 1950s, these changes that we measure in all components of the climate system are unprecedented over decades to millennia. And I think it's extremely important at this point in time to give as long as possible a historical context of the changes that we see. This is the second part of the first figure in the synthesis report, itself the subject of intensive debate at the approval plenary of the synthesis report. You see on the top panel the increase of the 3 most important greenhouse gases since 1850, with carbon dioxide 30% higher than ever in the past 800,000 years, methane higher by 140%, and also nitrous oxide showing increases. We highlight the longest living greenhouse gas in the atmosphere by the lower panel, which indicates the sources of these changes through the consumption of fossil fuel in gray, cement production and flaring, but also deforestation as a sizable fraction of the overall emission. And we also indicate that the correlation between the two time series is not a straightforward one by carefully changing the background color of the figure, but also giving more explanations in the figure caption as to the complex relationship between emissions and concentrations in the atmosphere. A complex relationship, by the way, that the science has clarified to a high degree of certainty. This evidence then collectively leads us to conclude that the human influence on the climate system is clear and that recent anthropogenic emissions of greenhouse gases are the highest in history. Now, looking forward into the future, climate change projections form an essential part of an assessment that shall be comprehensive. And here we show the result of an unprecedented effort by the scientific community through the World Climate Research Program, the projection of global mean temperature for the 21st century, using a suite of Earth system models in a concerted effort that provide us with hard numbers based on scenarios. For the simplicity here, I just highlight the two scenarios loosely called business as usual in red and climate mitigation in blue, which each show changes in the 21st century in this one metric of climate change, the global mean temperature, to reach an increase of over 4 degrees by the end of the 21st century for the business as usual scenario, or more precisely the RCP 8.5 scenario, whereas the climate mitigation scenario, the RCP 2.6, stays at 1 degree relative to the end of the 21st century and therefore has a high chance to limit climate change relative to pre-industrial below 2 degrees Celsius. Irrespective of that, we state and affirm that further warming will increase the likelihood of severe, pervasive, and irreversible impacts for people and ecosystems. And I've chosen this highlight statement to indicate and to illustrate the tight connection between the projections as they are coming from Working Group 1 and the studies and assessment of impacts for human and ecosystems. Let's look further on impacts which affect one of the important resources of humans and ecosystems, and that is land. You see here the increase of sea level, or the change of sea level since the year 1700. And this graph illustrates, in my view, very impressively what we mean by severe, pervasive, and irreversible impacts. If you look at sea level rise, as we have experienced it over the 20th century, an increase of 19 centimeters, to which humans have already adapted, compared this to a projected further increase of 63 centimeters over the course of the 21st century for the business as usual scenario. Now, adaptation to 19 centimeters is already a challenge, but it's an entirely different story to adapt to another 63 centimeters, indicating that limits of adaptation will be reached in many regions for such a large and severe climate change. And of course, there are also further changes, and I should here specifically mention ocean acidification, because in the public debate, when you talk about global warming, when we see messages in the media about global warming, this part of global change is often forgotten, and yet its impacts are only being studied now, and further studies will be extremely important, I think, in the course of the next assessment. You see here the projection of the change in ocean surface pH, which is stabilized under a climate mitigation scenario in blue, but further acidification on the same order of magnitude, if not larger, is envisaged for a business as usual scenario. Again, illustrating severe, pervasive, and irreversible impacts on people and ecosystems, many of which we are still about to learn and to quantify. For example, here, the change in food productivity or maximum catch potential, a figure that was included in the summary for policymakers of the synthesis report, indicating in red colors the reduction of that catch potential by up to 50% relative to today. I should preface this figure by saying that this is a previous scenario on which the study has been based, and the impact of ocean acidification itself on the catch potential has not yet been included, but I'm sure scientists will be working on that to produce results in the near future. But you do see on this figure also nicely that these changes affect regions in different ways. In particular, in the tropical regions where we see yellow and red colors, reductions in that food catch potential indicate very clearly that high challenges are ahead of us in regions which are particularly vulnerable to that change. This figure also illustrates the fact that these risks are unevenly distributed and are generally greater for disadvantaged people and communities in countries at all levels of development. This is another figure that illustrates in impressive manner the connection and the collaboration between the three working groups in the past assessment. And I'm very proud that we were able to pass this figure in the synthesis report summary for policymakers with the help of the scientific colleagues. Here, the near linear correlation between the cumulative carbon emissions and the warming in the 21st century, as indicated by the many scenarios that have been performed. Combine that with the assessment of 5 risk categories, from unique and threatened systems right to large-scale singular events, providing a very policy-relevant message regarding the risks that exist already today with the climate change that we have measured, and I have shown a few examples, but which exacerbates in the case of even holding the warming to 2 degrees Celsius. As you can see here, the risks at 2 degrees Celsius already are on the medium to high level here. The policy relevance of this combined figure is enlightened by the fact that if you, for example, declare a policy goal of 2 degrees Celsius, you can then read off, obviously with the uncertainties that are quantified during that assessment, the amount of cumulative total anthropogenic carbon emissions that are consistent with that policy goal. And finally, also a message, what does that mean with respect to the reductions that are required to stay within the consistent budget for the chosen target. In our case, we can affirm that in order to have a likely chance of reaching the 2-degree target, we require a reduction worldwide of fossil fuel emissions between 40% and 70% by mid of the 21st century. That necessitates a transformation in the energy sector, as highlighted here in this figure that comes from the assessment carried out by the 3rd working group in the synthesis and shown in the synthesis report. Essentially 2 pathways here to the time horizon to 2030, indicating that the share of the low and zero carbon energy part has to be increased in order to stay on these pathways by a large fraction if we peak emissions essentially today or in the next few years, and by a very large fraction of 240% by the year 2050 in the case of business as usual for the next few years. Irrespective of the scenario, we are looking at an energy system by the end of the 21st century, which is predominantly zero and low carbon energy. In other words, 95 or higher percentage of that fraction occupied by sustainable energy, which means that substantial emission reductions over the next few decades can reduce the climate risks, as was illustrated in the previous figure, and contribute to climate-resilient pathways for sustainable development. And here is an important keyword. I think this sentence here in the synthesis report is of key importance and goes far beyond the specific issue of climate change. Climate change is a threat to sustainable development, and the 17 Sustainable Development Goals have been evoked by previous speakers. I would argue that addressing climate change and the climate change issue will already bring us on a good path of almost half of the 17 Sustainable Development Goals. Not addressing climate change will actually make it impossible for many of these targets and goals to be reached. I think that's an important message that must come out of our assessment as well. And the seed is laid here by this very succinct statement: climate change is a threat to sustainable development. So with that, let's see. Oh, I'm going back, excuse me. With that, I'm actually already at the end. And I look forward that this nighttime picture will come to light in a few months, and that Paris will shine with a good agreement that the policymakers who are acting and deciding on all our behalf, but whom we inform by the science that comes out of the scientific community directly, but also through the voice of assessments such as that carried out by the Intergovernmental Panel on Climate Change, will reach a good end. So thank you very much for your attention.
Yeah, well, thank you very much, Thomas. That was really a very great introduction. I really like the slide at the end of the Eiffel Tower. Very symbolic. I should note the International Council for Science is very pleased to have its main offices in Paris, so we can look out and see that site. And we will be looking out during the Climate Convention meetings in December, and hopefully for years that follow, at our nice offices in Paris. It's also very good the way you brought together in the end the connectivity between climate change, sustainable development goals, disaster risk reduction goals, the importance of that science to policy role of the IPCC and the climate science community. And in that way, the Council of Science is also working together. We brought together, I think it was 60 or 70 global science advisors to a meeting recently, and this is part of our role to make that continue to happen. So thank you very much. That was excellent, and I won't go on to the rest of my story, but Anyway, I'd like to next introduce our next speaker, who will talk about the future of climate change science. This is Professor Sandrine Bony from the Laboratoire de Météorologie Dynamique at the Institut Pierre-Simon Laplace in France. And so I welcome you to take the speech. Thank you.
Thank you very much. Good morning, everyone. I would like to thank as well the organizers for all the hard work they've done in organizing this conference, especially the high-level organizing committee, but also all the technical staff that worked very, very hard over the last months to make it happen. So as Thomas has just presented a very nice overview of the state of knowledge of climate change science, and this state of knowledge will be a very good basis for the international negotiations on climate change, and hopefully there will be a good agreement that will be reached later this year in Paris. What I would like to do in this presentation is to think a little bit beyond the end of this year and look over the horizon and think with you about some of the scientific challenges that our climate community in research will have to address if we want to strengthen even further the quality of the future assessments on climate change. In the past years, the climate community has answered a few big questions on climate change. Questions such as, is the atmospheric composition changing? Is climate warming, and are human activities responsible for it? As you've heard by Thomas, these questions have been answered and the response is yes, yes, and yes. And having answered these questions in the affirmative now raises many, many new questions, as we would like to know more specifically how our climate will change in the future. Oops. And so now we have to address new questions such as how will global warming evolve in the future, not only on the long time scale, but also on the scale of a few decades? Or how will climate change not only globally, but also region by region? And how will that affect rainfall or extreme events, air quality, etc.? And we need also to assess how will climate change will impact ecological and social systems. And obviously there are very challenging questions for the science, but even if we could answer or could provide some partial answers to these questions, it would be tremendously useful for the society to help assess the risks of a dangerous climate change in the future, and also to think about the options in terms of mitigation or adaptation policies that might help to reduce these risks. There are challenging questions, and they are even more challenging because we have entered an uncharted territory. As it's been said earlier, the ice core data show that the CO2 amount concentration that we have in the atmosphere today, that exceeds 400 ppm, has not been reached for more than the last 800,000 years, and likely much more. And the rate of increase in the recent past has been extremely fast. And we don't know any analog for this in the past. So we don't have any analog for the present, and therefore we have to figure out what will happen in such conditions. We are really living an unprecedented geophysical event. And in climate change science, like in many other scientific disciplines, the state of knowledge looks like a giant jigsaw puzzle with many pieces of knowledge. And some of those pieces are already well placed, and it's what we consider as robust knowledge. Those pieces we are confident in them because they are supported by many different lines of evidence. But there are also many other pieces which do not fit yet within this puzzle, and that correspond to uncertainties, and sometimes key uncertainties in our assessment of future climate change. And obviously, those uncertainties matter, because when it comes to assessing what we should do in terms of adapting or mitigating climate change, then obviously if we overestimate the risk of climate change, or if we underestimate the risk, in both cases we might take decisions that might be harmful or dangerous for the future generations. So we really have to reduce those uncertainties as fast as possible, and there is urgency really. But the question is, how can we accelerate progress, and what's the most efficient way to do that? And that's a question that the WCRP, the World Climate Research Program, had in mind for the last years. And the response of the World Climate Research Program has been to identify a few grand challenges, which are initiatives that whose aim is to promote research on critical gaps of knowledge, and to focus efforts on specific questions for which, if we had answers, we would significantly advance the field. And it will be done by integrating many different communities around key questions, science questions, where new opportunities raise the possibility of breakthrough or rapid progress. So at this date, 5 such grand challenges have been identified and are ongoing, and some they relate to the melting of ice, to sea level change, to water availability, climate extremes, clouds, and climate sensitivity. And 2 other grand challenges are currently under consideration that will likely focus on the decadal prediction of climate and on the role of carbon aerosols and chemistry in climate. And the reason why we think those grand challenges can really accelerate progress in climate science is that they will focus on very specific science questions that will be addressed by integrating different approaches, because integrating different approaches is more powerful than just following a single one. So it will integrate analysis studies, observational studies, modeling studies. In terms of analysis, those grand challenges will focus on specific questions, and we'll try to test key hypotheses, which, once tested, could really advance the field, our understanding of how the climate system works, and would help to really improve future climate change assessments. In terms of observations, this hypothesis will be tested by using as much as possible the current observing system, and also proxies for past climate changes. But they will also try to fill the critical gaps in our observing systems, and there was a symposium a few months ago to talk about this, what needs to be done to fill these gaps. In terms of modeling, those grand challenges will exploit and use a large hierarchy of models, because there is no single model that can respond to all the questions, and we need to have a hierarchy of models of different resolutions, different complexities. The grand challenges will also address the model biases that limit the predictive capabilities of the models. And they will also imagine experimental frameworks that will help to tackle the key questions. And among those frameworks are CMIP6, which is an ongoing project of the World Climate Research Program. CMIP6 is the next phase of the coupled model intercomparison project. It's a huge ensemble of experiments, numerical experiments, global simulations of the Earth system, which are coordinated internationally, and that will be run by many models developed in many, many countries. And the advantage of having so many models is that then, by comparing the simulations together, we can better assess what is robust in the results and what is more uncertain, and we can learn a lot about how the climate works. So the CMIP6 will include many different experiments that would look at many different aspects of the climate system and of climate change. They will address the role of clouds, aerosols, chemistry, the carbon cycle, the land surface, snow, etc., in the climate system. They will really focus on many different scales and aspect science questions of climate change. And the experiments have been designed in such a way to address as well as possible the different questions that will be at the focus of the grand challenges. So CMIP6 will consider many models and experiments, and they will also consider a range of socioeconomic scenarios that will explore different plausible futures. So there will be scenarios of business as usual scenarios, but there will be also a range of scenarios assuming different levels of mitigation actions. And based on all this ensemble of simulations of the future, of course, the simulations will play a very important role in the next assessments on climate change, including for the IPCC. So in the next years, these grand challenges will help the climate community to focus on a few important questions, which are important for the science, but are also very relevant for the society. And there are obviously many different pieces of knowledge on which we would like to see progress over the next years. What I'd like to discuss to argue in this presentation now is that there are some pieces of knowledge which are fairly central in our understanding of climate change. And if we could make progress on this, it would really serve many other pieces of knowledge. And this piece of knowledge is the understanding of how the atmospheric and oceanic circulations vary and respond to warming and many other perturbations. If you can launch the animation, there is, okay. So this morning, I was hoping to show you very nice animations, but it's always risky to use animations in a presentation, and so you will have to imagine this thing moving, and you have to imagine in your mind. This is a picture of the atmospheric motions as visualized by the atmospheric water vapor in the atmosphere, as seen by the Meteosat satellite. And you can see many features when you look at an animation of this. You can see that the atmosphere is always in motion, obviously, and there are many different scales of motion. There are large-scale motions that control the position of the wet and dry areas on the globe. There's the dry areas are the dark areas that you see on the screen. If you look higher up in latitude, you would see that, well, we cannot see them, but you can imagine the weather system and these big eddies that organize and that control our weather in middle latitudes. And in the middle of the picture, the white blobs correspond to deep clouds and that form, that propagate, that eventually dissipate and sometimes produce some extreme events like tropical cyclones. And so the atmosphere is always in motion, and it controls many, many different aspects of our climate, as I will come back later. Here as well, I was hoping to show you a beautiful animation of the ocean surface currents predicted by a high-resolution ocean model. And that would show you that the ocean has many different scales of motion. There are very fast motions that quickly respond to the atmospheric motions above it. And there are very much slower motions, like the Gulf Stream or the equatorial waves in the tropics, that are more tightly linked to the internal dynamics of the ocean. And as you can see, maybe there are plenty of eddies everywhere in the ocean, eddies which have a very small scale. And nowadays we are living in an interesting time because we are developing new models of the atmosphere and of the ocean, models that can resolve both the planetary scales but also the very small scales, which are eddies in the ocean, which are clouds in the atmosphere. And now we really have an opportunity to better understand how the small scale and the large scale interact with each other and really better understand what controls the circulations. But in fact, many of the big questions on climate change that have been answered so far didn't really consider explicitly the circulations. Rather, they could adopt a more simpler and thermodynamic view of the climate system, a view that focuses on the global mean energy budget and its impact on global mean temperature and a few other quantities. And that's an approach which is very useful, and we still have a lot to learn from this approach. But to answer many of the new questions that we have to address now, we will have to develop in parallel a more dynamic view of the climate system, a view that considers how the atmospheric and oceanic circulations interact and are affected by global warming, but also feedback on the global warming and many different aspects of climate change. Obviously, thinking of the climate system in terms of circulation systems is not something new, and during the 20th century there were many scientists, including Ed Lawrence, that helped to understand what controls the circulation in the atmosphere and in the ocean. But now climate change poses really only new questions about the circulations, because now we have to address questions such as how do the circulations respond to the increase of greenhouse gases in the atmosphere, to the change in the evolution of the ozone hole, and to changes in aerosols, to the changing Arctic, and so on. We also have to figure out how the circulations vary, not only on the short time scales or the weather time scale, but also on much longer time scales, and to figure out what impact it has on the energy, water, and carbon cycles. So in the following, I will try to illustrate through a few examples why these questions are very relevant to the questions we are asked to answer now. Decadal temperature changes, for instance. If you have a thermodynamic view of the global system, the climate system, then you can predict why the Earth on average is warming, and probably by how much roughly it is warming. But it's much more difficult to predict the large fluctuations that observations reveal if you look at the rate of global warming with time. There are periods where the rate of global warming is quite fast, and other periods where the global warming is much slower, like we've seen, for instance, over the last 15 years. And recent research suggests that these modulations in the rate of global warming are very much related to how the circulations behave. In particular, the last hiatus period, the last 15 years, where we had a slow, weaker global warming seems to be related to changes of the atmospheric circulation over the Pacific, its interaction with the oceanic circulation, and the ability of the ocean to absorb heat. So if we want to predict the evolution of global warming over the next decades, it's very important to understand how the atmospheric and oceanic circulation behave. Carbon sensitivity. As you probably know, the rate of increase of CO2 in the atmosphere is about half the rate at which we emit CO2 in the atmosphere. And the reason is that there are large sinks of carbon in the ocean and in the land, in the biosphere. And from a thermodynamic view, we might expect that as the CO2 increases in the atmosphere, the strength of the carbon sink increases as well. But actually, it's not what the observations show. And the observations reveal very large variations of the strength of the carbon sinks at the decadal scale. And research suggests that these modulations are very much related to reorganization of the atmospheric circulation and how that affects the ability of the carbon to be absorbed by the ocean. So to understand the global carbon cycle, it's very important to understand circulations. Climate sensitivity. As you know, it's been a long-standing source of uncertainty in climate change science for more than 30 years. There is still a large uncertainty in how much global warming is associated with the doubling of CO2. And this uncertainty has large implications for estimating the amount of CO2 emissions which are compatible with a given temperature target. It can explain uncertainties that go up to a factor of 2, for instance, which is really large. But recent research has identified where this key uncertainty was coming from, and it's mostly coming from the response of these low-level clouds, shallow clouds that form almost everywhere over the ocean. In some models, these low clouds disappear very quickly as climate is warming, and that produces a high sensitivity of the climate, while in other models, these clouds do not change much, and that produces a low sensitivity of the climate. And what the recent research suggests is that understanding how these clouds respond to warming amounts to understanding how clouds interact with the circulation, the atmospheric circulations at the large scale, but also at the small scale, and that's really critical. Sea level change. We know that observations have shown that the sea level has been rising over the last decades, and models predict that it will keep rising in the future. But what's interesting is that the projections suggest that the sea level rise will not be uniform geographically. There will be very large regional variations. Look, for instance, over the Northern Atlantic, how much contrast you have between the different coasts. And these regional variations depend on many different factors, but what's clear is that the role of the atmospheric and oceanic circulations in shaping these regional variations is very large. Rainfall. We cannot overemphasize the importance of predicting changes in rainfall in the future. And there are very large contrasts in the distribution of rainfall in the present-day climate. There are wet areas, which are the blue that you see in this picture, and there are very dry areas, which are in white. And at the first order, the distribution of the wet and dry areas are controlled by the large-scale atmospheric circulation. And we understand better and better how a global change in temperature can affect precipitation at the regional scale. But what we do not understand, or very much more poorly, is how changes in the large-scale circulation can affect the distribution of rainfall at the regional scale, and how that interacts with surface conditions. So, for instance, controlling how the position of those rain belts in the tropics or the position of the storm tracks that control the precipitation at middle latitudes will change in the future is extremely important. Just a small shift of those dynamical features can have a huge impact on the rainfall at the regional scale. And those correspond to very exciting questions of basic science. And if we make progress on these issues, really, we can really advance many other issues of climate change. Extreme events. Probably the change in extreme events is one of the ways climate change can affect societies so much. And as you might know or not, is that most of the extreme events are primarily driven by particular atmospheric circulations. And the thermodynamics can help us understand why and how the frequency and the intensity of some of those extreme events could change in a warmer climate, and how that depends on what's going on over the land or the ocean. But what we understand much less is what controls the circulation patterns that are good for producing extreme events, if I may say so. And what controls the propensity of the atmosphere to organize into clusters or storms, or to produce atmospheric circulations such as blockings that are responsible for many extreme events, as those who have followed the heat wave we had last week in Western Europe know. Those are really exciting questions, and there are new theories, concepts that allow us now to tackle this question in a completely new way, and I hope that we can make progress on these issues. So we have plenty of opportunities for future progress on these issues if we really develop both this thermodynamic but also dynamic view of the climate system. And these opportunities are very diverse. They come from advances in observations, in modeling, in technologies, in the maturation of our thinking, and of ways on how we think about what affects the circulations, how it depends on clouds, on the land surface, on ocean eddies, on aerosols, and so on. So in conclusion, climate science has never been more relevant as it is today, and it has already answered big questions, and certainly now it's embarking on new grand challenges. And there are many pieces of knowledge that need some improvement in the future, but certainly there are some pieces of knowledge that matter much more than others, or very much, because they connect to so many different other pieces of our knowledge. And certainly understanding how the atmospheric and oceanic circulations behave, how they vary, how they can respond to anthropogenic perturbations, is certainly a clue for the success of all the grand challenges we have. And I'd like to finish by emphasizing the fact that the urgency and specificity of the societal demand is in no way incompatible with investment in basic research. I think that, on the contrary, it's really our best chance to really accelerate progress, because very often experience shows that it's really by tackling problems in a completely new way that you can really make fast progress and make old-standing problems finally tractable. And it's also our best way to prepare ourselves to explain in future surprises that our climate will inevitably exhibit in the future, which is what we expect in an uncharted territory. Thank you very much.
Well, thank you very much. Very informed presentation on both the challenges but the opportunities, in the sense, as you say, of the building upon fundamental science in the end to make things different for people in the future. So thank you very much. I'd like now to, well, first of all, thank the keynote speakers, but invite the highlight speakers to come to the stage. And do we know where is Michael Grubb here somewhere? Oh, there, okay. Yes, so what we're going to do now is hear presentations, let's say, in the broader science issues. Now we're going to deal with the warming of the Arctic and the global consequences, the going to the global input of climate change, and then really talk about the very important issue of emissions, their history and their future. So I'd like, first of all, to invite Vladimir Kattsov from the main Geophysical Observatory of the Russian Federal Service for Hydrometeorology and Environmental Monitoring. Vladimir.
Thank you, Gordon. Still, good morning, everyone. And let me spend 2 seconds for thanking the organizing committee and the technical staff for excellent arrangements. And I'm really pleased to take part in this conference. does it work? Oh yeah, it works. So if something like a big book of climate metaphors existed, then a separate chapter, I think, would definitely be devoted to the Arctic. And here are some metaphors from different times. The first one, the weather kitchen, which is the Arctic, goes back in the 20th century. It was before the beginning of my career in the Arctic research. The second one, a cannery in the coal mine, as far as I remember, as far as I know, appeared in the beginning of this century around what was called Arctic Climate Impact Assessment. And the last one, ground zero for the climate change, is actually the title of my today's talk, which was suggested by the organizing committee to me originally, which I decided to change for what you saw the previous slide, but still it made me think about metaphors as a background of my highlight talk. Arctic is indeed a champion of the global warming, and this is a very well-known, robust result which was assessed by all IPCC reports from the very beginning and by other reports as well, and even before. And this robustness is accompanied by another robustness, which is the tremendous intermodal scatter in the Arctic projections and Arctic simulations. So this championship, this leadership in the warming is supposed to be a result of a number of mechanisms and feedbacks altogether known as the polar amplification. If we were to characterize the warming Arctic in brief, in just few lines, we would probably note that, as already said, Arctic is very likely to be warming this century faster than the global mean. Arctic is among the most vulnerable to climate change regions in the world, and Arctic warming may have significant feedbacks on the global climate. And also, obviously, Arctic is indeed difficult to observe, to model, and to predict. After the impressive and encouraging success of climate science, which in particular has been demonstrated by the IPCC assessment reports and other climate assessments, one might get an impression that the physical basis of the climate science is more or less accomplished, and only minor details are to be clarified, which are of not that tremendous importance for the policymaking process. As a matter of fact, our knowledge of mechanisms of climate change still suffers from significant gaps and uncertainties, and Arctic is definitely not the least in this context. Sandrine Bony has very helpfully talked already about the World Climate Research Program's grand challenges, so I'm not going to repeat these, but the next slide is devoted to what is supposed to be open questions concerning the warming Arctic. I should say that quite a few of grand challenges directly relate to the Arctic and to the open questions I'm going to briefly comment on. So one of these is evidently the prospect of ice-free Arctic Ocean. In other words, how soon the Arctic sea ice may become seasonal, and there is quite an uncertainty about this very important issue. The other one is the strength of positive feedbacks between the warming climate and natural emissions of greenhouse gases from the thawing permafrost. How soon significant emissions may happen, and how much of the carbon sequestered in permafrost may become available for the atmosphere. The other one is, another one is the role of the Arctic Ocean freshwater budget changes for the global thermohaline circulation. How soon and how significantly the increased export of freshwater from the Arctic can affect deep water formation in the northern North Atlantic. Then, of course, very different timescale, but still the role of ice sheet dynamics in amplification of ice sheet's contribution to the global sea level rise. Can, for example, ice sheet dynamics of Greenland, which is not accounted in the state-of-the-art comprehensive climate models, significantly accelerate the melting of the ice sheet and therefore the sea level rise? The warming of the Arctic in connection with high-impact weather in the Northern Hemisphere, to what extent recent extreme heat waves, cold waves, floods, droughts may be connected with the warming Arctic. And on the top of everything, polar predictability, a particularly difficult scientific problem on the timescale from a season through a decade, having in mind the vigorous unforced variability of the Arctic climate system. A separate interesting question here is whether we are losing some predictability in the Arctic with shrinking of cryosphere. But it's not only physical climate that the warming Arctic has a potential to impact far beyond the region. And here I am entering the territory of tomorrow's day of the conference. Anyway, here are just, well, this is sea ice in two scenarios from the last generation of climate models through the 21st century. And here are just a couple of widely used examples for the economy. The prospects of northern sea route and of the access to the treasures of the Arctic shelf are breathtaking. However, possible positive and negative effects need much better quantification than we have now, and not to forget about accompanying non-climate impacts, such as environmental pollution, for example. We need to know when and what we should do to efficiently and proactively adapt to the warming of the Arctic. And here is indeed another vast field for scientific research. The use of climate model outputs in practical applications is a significant scientific problem, particularly pronounced in the Arctic, with already mentioned its internal variability and intermodal scatters. So model projections can be useless or even misleading if used improperly. The scientific problems of model data use in impact studies and risk assessments include approaches to model discrimination, to developing strategies for model ensembles and associated probabilities and uncertainties, evaluating added value and added uncertainties of downscaling techniques, different confidence in model projections of different climate variables, and so on. A key question here, what can climate science suggest now to users in various sectors in the warming Arctic, and what cannot yet? And what should be done to improve the situation in the near future? I have only 1 minute for conclusion, so I'm coming back to the big book of climate metaphors. A beautiful one goes back to the end of, very end of the 19th century and belongs to Jack London. The title of one of his sad short stories, The White Silence, is, to be more precise, it's more environmental than climate metaphor. Anyway, with what we have already just touched, how much of this metaphor is going to survive throughout the 21st century, and how much of something like red, brown, or purple noise will replace the white silence of the Arctic in our common future under changing climate. To some extent, this depends on us today and on the Paris events in December this year. Thank you very much.
Well, thank you very much. As we say, the Arctic, from let's say countries like Canada, Russia, of course, feel very close to it, a big issue. So let me move on now to the global input of climate change on ice. Camille Parmesan from University of Texas in Austin will be our speaker. Thank you. If I can get all this stuff.
I'm actually primarily at Plymouth University in the UK now, and it's been a very pleasant shift to come to Europe, where climate change research is much more mainstream. So to understand the impact of climate change in the future, I think it's very important that we understand what's actually already happened, what's already been observed. We've seen quite large responses to relatively small amounts of warming to date. And the changes we're seeing, they're not only a clear indicator that climate change is altering life, but it also gives us insight into what we can expect into the future. Now, to date, there have been 5 major, I tried to press, I have to press more slowly. To date, there have been 5 major global meta-analyses exploring the observed changes in some 4,000 species spread across diverse groups on every continent and every ocean. And overall, about half of all species have changed where they live, changing their distributions to track a shifting climate, and about 2/3 of species have changed when they live, altering the timing of spring events to track a shifting temperature window. And results are very similar across these studies. If you look at the last column, you see that anywhere from 82 to 92% of the changes observed are consistent with local or regional climate change, which have been some very strong numbers which have gone into the attribution section of IPCC. Now, in an absolute sense, the land has warmed quite a bit more than the oceans, and as we've been hearing, the Arctic has warmed more than the rest of the world, and you see that the tropics appear to have had very little change. But there's another way of looking at climate change, which is to look at something called the velocity of climate change. And what this is trying to get at is that if you're in the oceans, you have to travel a very long distance before you get into a different temperature regime, much further than you have to travel on land to get the same amount of temperature difference. So as the sea warms, a sea urchin has to move much further to maintain a constant temperature environment than does an animal or plant that's on the land. And the movements of these lines of temperature, or isotherms, or velocity of climate change, is what's being shown here. And this gives you a very different picture of what's happening in the world. So in particular, we have large parts of the Arctic that are having very little change, and much of the tropics is changing very, very fast. So viewing the world in this way gives you a different set of expectations then about how life will respond. And it's no surprise from looking at this view that you're seeing much faster changes in the oceans that match the marine velocity of climate change than you're seeing on land. So we're seeing, on average, 75 kilometers per decade poleward shifting in marine systems, matching velocity of climate change, compared to a much slower rate of movement, 6 and 17 kilometers per decade poleward shifts in terrestrial systems. But these averages actually hide the fact that you're getting some much more extreme changes. So for example, Atlantic cod has moved more than 200 kilometers in a decade. This diatom has moved more than 400 kilometers in a decade, and when you look at those extreme movements, you're actually seeing equally fast movements on land, with many butterfly species moving several hundred kilometers. Now, these extreme changes, it turns out, also seem to be predicted by this metric velocity of climate change. So if we look at the seas around Europe on the left-hand side, the velocity of climate change predicts rapid movement out of the North Sea and through the North Sea, shown in those blue and pink colors, and relative stability up around Iceland. And this very closely matches what we've actually observed the Atlantic cod doing. If we look on the land masses in Europe, you see that the Baltic is expected to be a barrier to movement, shown by these red dots, but if they can get into Sweden and Finland, you expect fairly rapid movement. And again, this is exactly what we see in the purple emperor butterfly. It took it 10 to 20 years to cross the Baltic Sea after warming began and get into Sweden and Finland, but once it managed to establish in Sweden and Finland, it went another 200 kilometers in just 5 years, colonizing northward at a very, very rapid rate. So we're also seeing that cold-adapted species, polar species we've already heard about, but also mountaintop species, they don't have anywhere to move, so they're being continuously restricted to smaller and smaller areas in higher and higher mountain peaks. For example, the Apollo butterfly in France has gone extinct on all mountain peaks below 1,000 meters, and it's only now exists in mountain peaks that are higher than 1,000 meters. So mountaintop species, like polar species, really do have nowhere to go. The other major type of change that we're seeing are changes in timing. Principally spring events is what we have most data on, and the groups are changing at different rates. So amphibians are advancing their breeding at the fastest rate, 8 days per decade. Birds and butterflies are advancing faster than our plants. And remember that many butterflies eat plants as their host. And in the marine systems, we see something similar. Predators are advancing faster than are their prey. So we're seeing suggestions that species that normally are interacting may be getting increasingly out of sync. Now, what I've been showing you is really the dominant responses that we're seeing. But in every data set, there are some species that aren't changing at all, and there are others that are going counter to what you'd expect. So for instance, in looking at this large database, several hundred species of flowering plants in the UK over an almost 50-year period, we see that there are some that aren't changing very much. And in general, the meta-analyses that I've been talking about just focus on the extremes that go in sync or out of sync with what you expect from climate change, and the response is overwhelmingly that they're changing with climate change. But it's always made me curious, what about these zeros? Are they really not responding to climate change? So we decided to do a much more sophisticated analysis, looking at responses of these plants, not just to spring temperatures, but to temperatures throughout the year and the year before. And in doing this, what we found is that most of them, some 3/4 of these species, really do only care about spring temperature. And if spring is warming, they advance their flowering. And if you look at the overall change over 50 years, you see that the mode is an advance of 1 day per decade. So that is the norm. But there's this other set of species that ends up being about 20% of the total that's doing something much more interesting. So as you can see, with the mode of 0, most of these are not changing their flowering. Does that mean they're not responding to climate change? It turns out that's not the case. It turns out this 20% of species actually needs winter chilling in order to tell them that winter is over and that they can begin spring. And when you have a winter that's too warm, they never get that cue. They don't get cold enough, and they keep thinking there's winter coming, and so it causes them to actually delay their flowering. But in the converse of this is that they're also sensitive to spring warming. So if you have a cold winter and a warm spring, they will advance their flowering. So very complicated. The observed change, which is what I'm showing here, is actually the sum of these two opposing drivers. Warming winters driving them to delay flowering, warming springs driving them to advance flowering, and thus most of them showing no change at all, and quite a few of them that winter chilling is more important than the spring warming, and so they end up significantly delaying. So what does all this mean? Well, this is just one data set, but it's a very strong, convincing analysis showing that many of the species in those big meta-analyses that have been classified as non-responders or stable or even going counter to what you expect from climate change actually are responding very strongly to climate change, but simply in a more complicated way than what we expect. So an older, simple analysis of this data set indicated that 72% of species were responding to climate change by advancing their flowering. This new analysis, more sophisticated, indicates that 90% of species actually are responding to recent climate change. So the moral of all of this is that our previous analyses that have been very simple ones in general are likely to have underestimated the proportion of species that actually have been impacted by recent anthropogenic climate change. Thank you.
Thank you very much. We've seen another example of both the complexities of the way in which science can lead to understanding of the, let's say, what's happening on this complicated system we call planet Earth. So our next speaker will talk about another complicated part. It's related to humans and emissions. So Michael Grubb, who is from the University College London, will speak on emissions, history of energy use and emissions. Sorry.
Thank you very much indeed, and delighted to see so many people here, and also honoured to help represent, I guess, the extent to which climate change is fundamentally an interdisciplinary field and challenge, encompassing also energy, engineering, economic issues. Now, in addressing the topic I was asked to cover, I really want to offer 5 main points as I work from the broad perspective on energy and environment, energy and development, through a brief look at key points on patterns, projections, and costs, before zeroing in on some data from the last 50 and then 5 years, and potentially new points around what may be a pivotal period of transition. Now, on this chart, it stresses basic industrial development requires energy. I hope that's not a surprise. Always has, I think always will. What it shows vertically is per capita energy demand, plotted against horizontally per capita income. What you can see is there's a big straight line, which summarizes the common perceptions. So it's not a one-to-one relationship between the two. Now, there's a great literature which probes the role of energy in development. I've indicated a few key authors there. But from a climate change perspective, this is also potentially a rather misleading kind of mental map. First of all, it's a log-log plot. So with a scientific audience here, you probably well understand it's not that difficult to generate something that looks rather like a straight line. In fact, the big variations between countries, which I've shaded out in the background, imply really quite big variations over time and between countries. And also, emissions are completely dominated by the top right-hand corner. Broadly, countries that have reached about $10,000 per capita income or higher, and for orientation, most of the rich world is now averaging over $30,000 per capita, which is actually very close to where this straight line ends. And my key message is when we look more closely at all of this, the whole thing starts to look rather more interesting. So if I move briefly on to the pattern, there's no question basic industrialization means lifting countries out of an energy world which is dominated by agriculture, traditional households needs and fuels, until industrial production, which is the top right hand, peaks usually close to around 50% of total energy needs, and typically in the region of up to $10,000 or so income level. But then in what's been dubbed the production to pleasure shift of energy, per capita industrial energy demand declines relatively as transport and other services grow. Now that's helpful and important because frankly, we have far more leeway over both the efficiency and the carbon intensity of most transport and services demands compared with, if you like, basic industrialization, pouring concrete, steel, etc., for infrastructure. And that's done interesting things to our ability to project. Because that transition, which broadly above 10 to 20 or so dollars a capita, has been historically associated with a tendency to also hugely overproject energy needs. On the left hand here, we have a rather famous diagram in the energy world of the projections of US energy demand for the year 2000 that were made in the 1970s. And reality in the year 2000 turned out to be below the low end of the full spread of virtually all US energy projections. And it's been similar in the UK. On the right hand, I've been in this business for a while, you will gather. In the right hand, I've just illustrated that in 1990, the UK Prime Minister Margaret Thatcher was earnestly advised by economic modelers and lobbied by industry that greenhouse gas emissions were likely to rise about 30% over the decade. And many of those resisted her commitment to return UK emissions to 1990 levels. As it turned out, GDP grew by almost 30% over that decade, but UK greenhouse gas emissions fell by 8%. Trust me, that was not purely due to climate policy, although elements did help. If we now look at an additional point I wanted to offer around the costs of energy, because similarly there's a broad assumption that seems like common sense that higher energy prices leads to higher costs. Well, that turns out to actually be rather questionable when we look more closely. What I've plotted here on the vertical is a basket of energy end-use prices, and horizontally, the energy intensity of economies per unit of GDP, and then plotted various industrialized countries across that. And of course, national energy expenditure per unit of GDP is the product of prices and the amount of energy required, price times volume. The dotted line here shows the line of constant energy expenditure proportionate to GDP. What you find, for example, is that Japan, which has energy prices more than twice as high as the US throughout this measurement period, actually spent exactly the same amount, exactly the same proportion of its GDP on energy. And France and Germany are also bang on that dotted line. It's something that drawing upon research in two different arenas, I've called the Bashmakov-Newbery constant of energy expenditure. And it seems to be provoking quite a lot of analysis, discussion. The important point is that adjustment is not easy. And also, countries that have, however, tried to shield their citizens, for example, the former Soviet countries that heavily subsidized energy on the grounds that cheap energy was good for development, which are those circled on the right, have actually ended up spending much more on energy than countries that, if you like, face or addressed higher energy prices because of all the wastage and inefficiencies that tend to go with very low energy pricing. And it's what economists call satisficing. I'll have a chance to sort of talk about these policy-related effects and the price relationships in the energy transformation session on Thursday. So the message on all that is life looks more interesting when you look more closely. And what I'd like to now move on to is some caveats. Because important caveats around this. One is that adjustment takes a long time, but the other is the question, have countries that have had higher energy prices simply exported or outsourced their emissions. Well, I'm glad to say the IPCC, with this chart in AR5, tackled this in looking at the shares by major income groups of emissions over 1990 to 2010. Now, the brief summary that you will see in this chart is that the developing world overall, but dominated very much by the rapid rise in upper middle income countries, and notably, most of all, China, had a meteoric rise in emissions since the millennium, such that by 2010, the territorial emissions from developing countries easily exceeded that of high-income countries at the top there, the blue that had stayed relatively flat. But on the consumption basis, looking at the carbon footprint, that wasn't true. Up to about 15% of those emissions were in fact industrial production of goods from developing countries purchased by consumers in high-income countries, rather badly named as trade-embodied emissions. Of course, they're emitted, not embodied in reality. And this brings me to my final set of points, which is really the need to look more closely at interactions of development, trade processes at country level, not just the last 50, but the last 5 years. So in this chart, I've reverted to the vertical per capita emissions plotted against horizontally per capita GDP, wealth. Illustrated first with respect to the US, you see that it's, in effect, in the 1960s, dirt cheap energy meant that industrial dominated phase was extended and merged with an extremely inefficient transport system to peak in 1973, indicated there when the first oil shock broke. That caused a recession. The economic line goes slightly backwards. It took a second oil shock in 1979 to really break the trend, and that in fact, for 30 years since then, US territorial emissions have bobbed around just below 20 tons of CO2 per capita. You can also see the dramatic impact of the 2008 energy crisis. But emissions didn't only go down because of recession, they continued to go down as the US has emerged from recession. Now, what about the consumption? I hear you say, well, over that period, this other line shows the US moved from a net producer and exporter of emissions to a net importer. So its emissions footprint did continue to rise, albeit more slowly over those 30 years. But the financial crisis first hit imports, and US consumption footprint has gone down. And we see really a very similar kind of pattern in the EU, where you have roughly half the level of per capita emissions, somewhat higher share of embodied, but not sufficient to change the basic story, and per capita GDP generally 20 to 30% behind that of the US for most of that period. The upshot is that US OECD territorial emissions are now back to the level they were in the 1960s. Consumption emissions were rising, but are now about 10% below their peak of 2008. And to conclude, I see my time's just about up. Couple of key points about developing countries on the similar line. One of the interesting and hopeful things is the ways that some of the advanced emerging countries have gone past the $15,000 a capita threshold, still at much lower per capita levels, 2 to 4 tons per capita in case of Mexico and Brazil. But of course, all eyes are on China, which has seen a staggering growth rate, and yet, having appeared to be following the old course, if one calls it like that, everyone is still poring over data which suggests that China's emissions stopped growing last year, and collectively so did the world's. So that 2014, CO2 emissions stable, GDP increased 3%. Just to reiterate the concluding key points, energy is essential to basic economic development, but the pattern changes through the shift from production to pleasure. Model-based extrapolations typically wildly off, particularly during that phase of industrial maturation. The proportion spent on GDP has been remarkably constant, given time to adjust because of efficiency and innovation responses to higher prices. So that I've concluded, perhaps, the news is not all bleak. We may have seen a marked trend break in the last 5 years. There are new development patterns emerging with all of the questions and potentially opportunities that implies across the world. Thank you very much.
Well, thank you very much to the speakers in this session. If you can now depart, but Leah, having left us with the wisdom of how the Arctic and the global issues and how the species are, let's say, the various parts of our system, and then the, let's say, the challenges of economy and energy use at the end. We're now going to go to a panel discussion. If I can invite Maarten and Virginie to come to the thing. We're going to talk now about coping with disasters. This is a huge, important area. Each of our two speakers will give short presentations, then we'll have a panel discussion. And that will bring us, let's say, to the conclusion of this section. So, Virginie, are you going to speak first? I guess your PowerPoint's up, so go ahead. Sorry, Virginie is from the Laboratoire Littoral Environnement et Société, Université de Rochelle-CNRS, France.
Thank you very much, Gordon. Dear members of the scientific and organizing committees who make this important event possible today, dear all, as a coastal geographer working mainly on small island issues, I will try and address a few key messages for science to better support decision-making in avoiding maladaptation in the future. In the climate change context, coping with climate disasters requires to design policies addressing in a coherent way current and future climate-related risks for at least 4 reasons. First, because climate disasters result from the interrelated impacts on societies of climate viability and climate change. Second, because the impacts of climate-related extreme events will increasingly be influenced by climate change in the future. As a result, we have to acknowledge that both the nature, the frequency, and the magnitude of impacts and impact areas are changing. Third, because the increasing impacts of climate disasters on societies are also due to a rapid increase in human vulnerability that is likely to keep increasing in the future, notably in coastal areas. Fourth, because one key challenge when designing climate risk reduction policies is precisely to avoid maladaptation by start doing well what we currently poorly do. Many examples show that disaster risk reduction policies that reduce risks in the short term in fact exacerbate future risks. These can be highlighted by the negative impacts of coastal protection. Indeed, although the erection of massive engineering structures along shorelines has reduced the exposure of human assets over the past decades, it has generally contributed to increase long-term vulnerability by encouraging urbanization, accelerating sand dune and beach erosion, and weakening public awareness. The last 2 points show that vulnerability has become a key determinant of the severity of the impacts of climate-related events on societies. As a consequence, it is urgently needed to reduce vulnerability. But this implies that both the drivers and the processes controlling vulnerability and changes in vulnerability are properly understood. And yet, while these root causes of vulnerability are well known at the scale of specific regions, such as coastal areas at large, for example, here, we still have to take up major challenges to support in the most relevant way decision makers in avoiding maladaptation. Two key challenges that have to be addressed to avoid maladaptation are, first, to go beyond generally accepted ideas, and second, to acknowledge and document the high spatial variability of both impacts and vulnerability. These are the two key messages that I would like to share with you today, because I am convinced that they will have to be further addressed in future IPCC work. I will address these messages based upon a 20-year research experience in small islands that are, as you all know, highly vulnerable to climate change. So, why is it so crucial to go beyond generally accepted ideas to avoid maladaptation? I will take the emblematic example of the most vulnerable islands, reef islands. A generally accepted idea is that reef islands are currently eroding as a result of rising sea levels, putting them at risk of disappearance in the near future. This generally accepted idea has major implications on adaptation strategies at the national and international levels. It has indeed promoted the idea that there is an urgent need to protect island communities against climate threats by building massive engineering structures, implying that many settled islands could look like Mali in the future, and organizing the massive and inevitable international migration of these people. Most island countries and territories have built massive engineering structures of this kind along shorelines over the past decades and are still seeking for international funding, adaptation funds, to continue island fortification. And yet, what we have to acknowledge today is that the scientific studies conducted over the 5 past years have allowed going beyond this generally accepted idea of island disappearance, which has huge implications for adaptation strategies. As you can see on this slide, the measurement of shoreline changes on 191 reef islands demonstrated that 83% of these islands had either expanded or maintained their land area over the past 40 to 100 years in both undisturbed environments, as is the case of Grand Glorious, for example, in the Mozambique Channel, a French island, and in disturbed environments, as exemplified here by an example in French Polynesia. Such key results emphasize the major role of sediment production and accretion, which is driven by coral growth and hydrodynamics in reef island response to climate change. It shows that coral reefs have allowed vertical island adjustment to rising sea levels over the past decades. But of course, this good news doesn't mean that coral reefs are not at high risk of accelerated degradation in the next decades, and that island responses are not going to change in the future. It just highlights the fact that reef island disappearance is not for tomorrow, and that therefore island countries and territories have a leeway to think adaptation pathways, and that these adaptation pathways should consider the major role in coral reefs in supporting island resilience. Such important results have major implications for adaptation strategies. They emphasize the urgency of reducing the negative impacts of human activities on both coral reefs and coral environments, and to maintain accommodation space to allow vertical island adjustment where sediment accretion occurs. In such environments, building engineering structures of this kind would be highly maladaptive, as it exacerbates current environmental degradation by exacerbating aggregate mining and the disruption of sediment transport, for example, undermining the resilience of reef island systems. But of course, basing adaptation strategies on ecological resilience cannot be erected as a new general rule, because some reef islands are eroding and contracting, while others have expanded over the past decades but are no longer resilient. In those environments that are highly disturbed by human activities, as you can see here, other strategies, of course, have to be implemented. So, this single example shows that like other coastal territories, small islands exhibit highly differentiated vulnerability profiles, and that this has to be taken into account in the designing of adaptation strategies. It also reaffirms the crucial importance of improving knowledge on ongoing changes and of monitoring future changes to better support decision makers in relevant adaptation strategies. I thank you very much.
Thank you. Our next speaker will be Maarten van Aalst from the Red Cross, Red Crescent Climate Center in the Netherlands. Maarten.
Thank you very much. And I have the pleasure of standing between you and the lunch break, so I'll try and be brief. I just wanted to share a few perspectives from my role as director of a reference center in a big humanitarian and development organization. My team of about 25 people has the role of bridging science, policy, and practice. So while I spend part of my time interacting with this fantastic community here, and I've had the privilege of serving on several of these IPCC reports shown before, I also spend a lot of my time talking to local Red Cross volunteers working in small villages around the world, and speaking to policymakers that may not think about climate as their first priority, but are still affected by it. I also teach at two universities, IRI at Columbia University, one of our key partners getting climate information into the Red Cross Red Crescent, and at the STEEP program at University College London. And I just wanted to acknowledge also the amazing amount of new research that's appearing, not actually just from the climate change perspective, but more broadly about this whole notion of dealing with climate extremes, also from the perspective of the humanitarian community, also from the perspective of the regular development community, for instance, discussing resilience in the context of sustainable development goals. There are many people that are actually looking for many of the pieces of the puzzle, as shown so elegantly earlier, in their work, but may not necessarily come to get it from conferences like ours still, and may also not yet still speak the same language in which we're presenting some of that material. So I'll be focusing on 4 key messages. The first is the need to focus on risk as a concept that helps us cross some of these barriers. Then the second, to think across timescales, rather than zoom in on one particular element, either the short or the long. The third is to think more about decisions rather than just about the supply of information. And finally, the central need for communication. And I'll be highlighting that with a few examples. So the first point, it's all about risk. When we go around the world speaking to these local communities, they don't think about the end of the century, they don't think about scenarios, they think about what's affecting them right now. But they are aware of the climate, and they're aware of what they call funny weather happening to them. Now here's a more scientific approach. This was actually a graph that we put together for an actual workshop in a particular place in Sri Lanka, where probably thanks to a colonial presence there, we had a pretty nice long record of seasonal rainfall. And there you can see if you would have focused on the long-term average, you would have gotten it wrong. What matters here is what they're facing in terms of changing extremes, actually on both sides, and both intensity and frequency. Now the point here is that on the one hand, that's very valuable information to them, but they were also facing a rapid increase in population, particularly in the most vulnerable areas. So that brings me to that point on risk, and where I really feel that the AR5 cycle, and particularly the work in the special report on extremes that Gordon also was part of, that was then taken forward also in the Working Group 2 part of the 5th assessment report in this particular graph, was so essential. The fact that we were no longer separating the climate side, the hazards in the dark blue in this particular graph, but also looking very explicitly at those elements of exposure, what's at risk in that place where the hazard occurs, and vulnerability, how badly is it affected, and then try and understand all the feedback loops. That has really helped us bring a lot of new knowledge into this community, but also more effectively export the knowledge from all of you into other realms. The second key message, bridging timescales. And again, this is something that I think the scientific community is starting to do, trying to look at seamless forecasting from the weather timescale to the long-term projections. But you also see it happening in communities outside that are, again, looking for that knowledge. And one example, for instance, is the World Bank, which last year committed to a replenishment of IDA, their main window for the poorer countries, $52 billion of new investments, and a commitment to screen all of those for literally climate and disaster risk. So it's that combination that is now seen as the challenge that's in a way put in front of us. Because the question then, of course, is what science do they need to properly screen all of those investments? Another example in our own community, the Red Cross Red Crescent, is this concept of early warning, early action, where on the one hand, we're no longer responding after the fact, but we're also taking the anticipation from just a couple of hours before an event of a regular early warning into the much longer timescales, and indeed also trying to understand the ecosystems dimensions, for instance, from the previous presentation, in trying to address the risk facing these communities. Here's one example, seasonal forecasts, in this case a seasonal forecast in 2010, giving patterns of changed risk in a dynamic way for the coming 3 months. And here's some of the major operations that we had to conduct in the months thereafter. Now this is, and that's an important point about that sort of science, we heard a lot about uncertainties already. This is not a forecast of humanitarian problems. This is a forecast of, a probabilistic forecast of potential deviations in seasonal rainfall. And the translation between those is essential. And that brings me to the next point, linking science to decisions. In many cases, we're still in a supply-driven mode, providing information as it comes out of our models, rather than in the way that most effectively serves decisions. And often those discussions then center more around the sort of characterization of uncertainties, rather than at dumping more information. It often centers more on thresholds, rather than just the whole range of information. And in some ways, it's about communicating honestly about things that we do not know and will not know, rather than, I was interested in your example, Virginie, on the maladaptive risk of an overconfidence in a certain solution. I think we see the same, for instance, with downscaled climate information in certain places, where people have a tendency to believe the most downscaled model, even if we just know that it's actually dangerous to plan as if that were the certain future. So we still have a lot to learn there. And one example is, and that's actually very particular to the humanitarian community, which faces a strong incentive problem, that if the information is not certain, it's almost impossible to act before a disaster. Now, what we're trying to do is put in place what we call forecast-based financing, where we're actually acting on scientific information ahead of a disaster, but dynamic scientific information. And then very particularly asking that question, and we're trying to address this in very solid scientific methods, and those of you interested in that, there are several discussions happening this week on that. to try and address that question of what are the thresholds? What's the menu of pieces of scientific information across timescales? And what's the menu of actions that you can feed with that? And how do you then start coupling that science? Finally, communication is key. Here's an interesting piece. This is actually a press release from my own organization. If you look at the bottom there, you find an interesting link to our science partners at Climate Central. This is an analysis that we did in real time of the heat wave that's actually still occurring in part of Europe, but particularly happened last week. A group of scientists, the partners also include KNMI in the Netherlands, Oxford, Melbourne, and a range of specific partners for this analysis in Europe, bringing the data and their local perspectives. I'm not sure what's happening to the screen there. I hope you got that link. You'll be able to look it up later. The key point being that what we try to do is do the attribution of this heat wave in real time. So we actually forecasted the heat wave as it was unfolding, and then took the 3-day maximum temperatures in a rolling way, and then looked at the return periods of that, both in the observations in the last 100 years and in a model environment with and without greenhouse gases being added. And that allows us to then communicate, in this case in an IFRC press release, going to the humanitarian community about what we see as a problem right now that our volunteers need to address in terms of climate already affecting that risk. That's the moment when there's a very different appetite for that sort of information than when we would have published it a year later in a scientific journal. And this is one example. This is a broadcast meteorologist in Belgium in this case, who speaks about it on the evening news, and in very simple words is able to then make it relevant at the moment people are experiencing these disasters. And I think this is one of those exciting ways that we can organize our science better and be more timely, but also deal with those challenges of communication. On the one hand, doing the IPCC style, highly rigorous uncertainty languages for our internal purposes, but then also communicating clearly and allowing people like Jill Peters in this case to do her job. I'm about to finish, Gordon. This is another example, funny animations that help us get the story across in the Pacific. And finally, games that help people actually interpret the information that you all provide to us and then use them in real decisions in games, in this case in Namibia, where we use this with small villages, but equally in the White House. This is my colleague Pablo Suarez, responsible for much of that. More examples available here, and I look forward to discussing much of this with you over the coming week. Thank you.
Well, in view of the time, I think we'll have to forego our great discussion amongst the panelists, but as we point out, we have lunch coming and you'll all be able to sit down with these two speakers and talk with them and the others. I think just if I can have 2 seconds before you go, I did want to just say that a couple of the issues that I think were very importantly brought up there was this whole question of early warnings and actions, the decision-making based on science. The World Meteorological Organization has a program called Global Framework on Climate Services, which is aimed at providing this. The Council of Science and other co-sponsors has organized a program called Integrated Research in Disaster Risk. And one of the key things there is risk interpretation to action. How do people as individuals, how do governments, how do companies interpret risk, and based on that, how do they take action? And that means we need to better communicate those uncertainties or the certainties as we know them to build that sense. So I'd like to, in view of the time, and I can see Jean-Francois is getting ready to jump to the screen here. We will have an announcement in a minute, so don't leave your seats. Some important announcements coming up, but let me first of all say thank you to all of the speakers in this session. It has been excellent, outstanding, and thank you all.